Hello everyone, my name is Anthony Shivkumar, and in today's video is a follow-up based on the previous video, which is I'm doing a video log series on brushless DC motor. And I have been using hobby electronic speed controllers to control my brushless DC motor, and there's nothing wrong with it. But I want to create my own electronic speed controller for various reasons, but one being that I wanted to understand it at a deeper level, not just from a theoretical perspective, but also the implementation and how you can program the microcontroller to control the speed controller so that I can control this motor. So what I have in my setup right now is I have the pre-driver, which is now connected to the MOSFETs. And these are the three outputs of the MOSFETs, which is now connected to the motor from the other side of the PCB. This is the microcontroller. The microcontroller will now start to send the signals to the pre-driver, and the pre-driver will start to switch the MOSFETs based on certain logic. And that logic is on this piece of paper that I have over here. I'll explain to you as we go about this particular video. What else do I have over here? I have a motor, and the motor, just to make things simple, the motor has a stator, and the stator is the stationary part of the motor. And it's got 12 stator windings. This is not necessarily important, but at the same time, because the control of this motor is kind of agnostic to the configuration of the motor. But just to explain what's happening in my motor over here, we have 12 stator windings, and the stator needs to be divisible by 3 because there are 3 phases. And then we have the rotoring part, which is the rotor part. It's the outrunner because it's the outside part of the motor that is rotating, and it's got permanent magnets stuck onto it from the inside of this motor. On the rotor side, it's got permanent magnets, and it's got 14 permanent magnets stuck to it. I counted it, and it'll always be an even number because you need to have pole pairs. So 7 pole pairs, so that's 14 magnets. So it's north, south, north, south, north, south. The goal over here is to create a rotational mechanism, basically, so you make the rotor spin, and we need to activate the stator windings in such a way that we're creating a north south north south north south in the stator, which is a stationary part, so that the rotor, the rotational part, is constantly being attracted to the north south north south north south, creating the spinning action. That's what we're trying to do over here. Now, a traditional brushed DC motor that if you go to, say, any shop and buy a toy car, it'll have a brushed DC motor. If I just put batteries, it'll automatically rotate. And the process of creating this north-south, north-south, north-south effect is, it's called commutation. And the commutation over here is happening through brushes over here. But the difference is that, the difference between a brushless DC motor and a brushed motor is that this will wear and tear. It cannot go very high speeds. This can go very high speeds because I'm supposed to mount a propeller onto this, so that it can take off the quadcopter or a robot. Whereas a brushed DC motor will not be capable of going at very high speeds without significant wear and tear and losses. So in order to, though they're exactly the same, and from a physics standpoint, the controller is very different. And modern electronics is allowing us to control this motor using power electronics over here, and you need a microcontroller to do this. So that's what we're going to go about. That's what we're going to basically analyze today, and this is what we're going to try to control this motor over here. Okay. Now, on my circuit over here, I have I've got 6 MOSFETs. I got MOSFET 1, 2, 3, 4, 5, 6. So there's MOSFET 1 and 2. There's MOSFET 2 and 3 and 4, 5 and 6. So the first one is phase A, second one is phase B, third one is phase C. These are the 3 wires that are connected to the rotor, and this is phase A, phase B, phase C. So ideally what would happen is that you have voltage coming in, it goes through one of the phases, and then it comes out through the other phase, and then the circuit is completed. So the same thing would happen over here. It would flow through the MOSFET, it'll go through one of the phases, and it'll come back, and it'll come through one of the other phases. So that's what's really the idea of having this. And each time it goes through a phase, the direction of voltage through the phase will change the polarity of the stator windings. So if it's going in one direction, it would be positive. If it's going in the other direction, it would be negative. So this could be creating a north, creating a polarity of north, and then this would be creating a polarity of, say, south, north and south, or plus and minus. So the direction of the voltage is you can configure the direction of the voltage by changing the switching action of these MOSFETs. Okay, so just to show you how I have my oscilloscope, and in order for us to not just switch things randomly, we need to figure out a way to switch in a more logical manner so that we create a rotational effect. Because if you don't do that, what would happen is you could have a north-south, and it would just start stalling. We don't want it to stall. We want it to rotate properly. And in order for us to rotate properly, we need to have some form of logic in terms of switching, so that we're not switching randomly. We're switching in such a way that is creating the spinning action. And we do that through something called as back EMF. A back EMF is as I mentioned in my previous video, that a motor, when you're powering electricity to it to create generating a rotating action, is called a motor. But at the same time, when you create if you give it as a mechanical input, you can generate electricity. This is how dams work. You have these big major motors that, as you spin, will start to generate electricity. So a motor can be in one direction, it's called a motor, and the other direction is called a generator. And this generating action is called back EMF because we can measure that voltage. So to give you an idea, I got my oscilloscope connected over here, as you can see. And as I spin it, you can see that all three phases are now one. As you can see, they're all 120 degrees. That's their 120 degrees apart. And as I spin, it's creating some voltage. And the faster I spin, the higher the voltage is. As you can see, it gets higher and higher. All right. And this is what we're going to use. At voltage is how we're going to figure out where exactly the position is, so that we know exactly what to switch. Okay. In my timing diagram right now, what I have is the timing. We call these timing diagrams because they are talking about the time at which I am trying to synchronize and switch all of these components. Okay. So on the top, I have this is the top MOSFET. The bottom is called the bottom MOSFET. So this is phase A. So these both is phase A. This is phase B, top one and bottom MOSFET. And this is phase C, top MOSFET and bottom MOSFET. All right. So this is the graph. What I've also done over here on my horizontal axis, I've basically put in the degrees. So 0 degrees, 60 degrees, 120, 180, 240, 300, and 360. So this is 360 degrees is one rotation. But mind you, this is the electrical rotation. This does not necessarily correspond to the actual physical rotation of the motor. And to make sense of this is that the algorithm that we're going to implement into this rotor, into this microcontroller to control this rotor, can work with any brushless DC motor. So you could have 20 poles on your rotor. You could have 21 stator windings. It doesn't matter. We're going to create an algorithm that is agnostic with the configuration of the motor, and most brushless DC motors work that way. Okay. And what I'm about to show you is also called a 6-step commutation. So there are different ways of controlling this brushless DC motor. There's a sine wave control algorithm. Then there is the FOC, field oriented control. And then you have, in this particular case, 6-step commutation or trapezoidal commutation. So we're talking about the simpler one, which is called the trapezoidal or the 6-step commutation. And I'll get into why it's called 6-step commutation, because there's 6 steps basically to make it work. 1, 2, 3, 4, 5, 6 based on the angles that we have over here. Okay. So in phase A, when I trigger phase A, the voltage across the stator will be basically coming across. This is the stator winding of phase A. And then when I stop it, we have something called as the back EMF. Okay. So right now, when I don't have anything activated, this will be purely sinusoidal, as we saw in the oscilloscope a little earlier. But once I start to activate the stator windings, so any 2 phases will be activated. The third phase will now create the back EMF. So at every given instance, there will be two phases always activated. So in this particular case, when I go from 0 to 60 degrees, there's two phases activated. When I go from 60 to 120 degrees, phase A and phase C is activated. Then when I go from 120 degrees to 180 degrees, I have phase B and phase C activated. Then you have, phase A, phase B, and again phase A, phase C, and then we have phase B, phase C. As I mentioned, the top part is the high MOSFET and the bottom part is low MOSFET. So let's figure out what's really happening. So in order for me to rotate, I'm going to trigger the MOSFET high. So this is going to create and activate one of the stator windings to have, say, a positive polarity. And as I do that, it will start to create a spinning action. And while I create that spinning action, I need to activate a flow of current. There needs to be a closed path. So the closed path is it needs to go from one MOSFET, go through one phase and come back to the other phase. So I need to activate at least two MOSFETs. I cannot activate the same MOSFET in the same phase, because if I do that, then what would happen is I would short circuit the whole thing. You want the current to flow through the motor and then back again to the low side MOSFETs. If I activate, say, phase A and phase B, phase A, high side and low side, then I'll create a short circuit and very high current will go and blow up the whole thing. So we cannot activate phase A and phase A high MOSFET and the low MOSFET, because this will create a short circuit. We need to make sure that the current is flowing through the motor and not directly through the MOSFET. So in order for us to do that, we have the high side MOSFET on, current flowing, and then in this particular case, it's coming back through the phase B low side. So it'll come back to the phase B low side. So it's coming from the high side and it's going to the phase B low side. That's what's happening in here. And then after 60 degrees, once it spins a little bit, there'll be a back EMF somewhere. And in every phase, there'll be a back EMF. And this back EMF is what we're sensing. So when we see this back EMF, we know exactly what to switch. So while this is happening over here, we have a back EMF that's happening over here. So in every phase, there will be, in every angle basically of rotation, electrical rotation, there will be a back EMF. And once we know what the back EMF is, it says, hey, phase C is going as having a back EMF. So now we need to trigger phase C immediately. And as you can see, we have, this is high, phase B is off, and now phase C is high. And this is when we know when to activate phase C. And when we're activating phase C, now there's a back EMF in phase B. Now phase B is going high. So based on the direction of the back EMF, we know what exactly to trigger next. And then we trigger phase B. And we should always have one high and one low on. So in this particular case, we have one high, one low on. We have one high, one low on, one high, one low on. So at every given configuration, it will be a one high, one low, one high, one low. So that's really the idea of what's really happening. Based on the back EMF, I know exactly which MOSFET to trigger. Based on this back EMF, I know which MOSFET to trigger. Based on this back EMF, I know which MOSFET to trigger. And this will create one electric 360 degree rotation. Though this may not be a mechanically it might just spin, say 20%. It may not be, or it might be, say 25 degrees or 30 degrees, depending on, what the configuration is. But it doesn't matter, because it will continue to do this forever and ever till you ask it to stop. And this is all pulse width modulated. The reason being why it's pulse width modulated is because we can control the voltage. We're not controlling the height of the voltage basically in this particular case. So if I'm putting in 7.4 volts, that's my battery that I'm providing for my drones. If I'm putting in 7.4 volts over here, I expect it to be always 7.4 volts. But for me to adjust the voltage, because as I mentioned over here, that I can control the speed based on the voltage over here, I can pulse width modulate. And that's the reason why we have this pulses over here, because by pulse width modulating, I can adjust the speed of I can adjust the voltage. So 10%, so if it's 7.4 volts on, completely on, that means it would travel at 7,000 RPM. If I don't have the pulse, it will be traveling at 7,000 RPM. And in order for me to say rotate at, say 1,000 RPM, I just need to, approximately 10% of that. So by giving a 10% pulse width modulator, I can approximately, rotate it as say 740 RPM, or, and accordingly adjust the pulse width modulator so that I can rotate at the speed that I want. This is how you control voltage. Okay, so this is how the voltage is controlled by pulse width modulating. And then this graph over here will automatically show you the amount of voltage that is flowing into the stator winding. Okay, so this over here is all the stator winding and the amount of voltage flowing. So when this is on, and then when it's off, we have back EMF. Then this is on by the negative side, and then when it's off, there's back EMF. So when I'm writing the software for this particular microcontroller, what do I need to consider? So from an embedded standpoint, what do I need to activate in my microcontroller? I need to activate my pulse width modulators. I need to activate my analog to digital converter, because there's two ways to analyze this back EMF. So when we're going at low speed, I can do something called the integration method. And integration means area, okay? Integration is nothing but area. So I can calculate the area of this graph. And once it reaches a particular threshold, I know exactly when to switch. And this works when it's in low speed, because in low speed, you can basically think of this taking a longer time. As I mentioned, this is in degrees, right? But this degrees could correspond to a certain time. It could be, 10 milliseconds, 20 milliseconds, or 30 milliseconds, depending on the speed of the motor or the rotor, right? So this can be adjusted based on the speed of the rotor. So if it's going slow, then this will be the 60, going from 20 degrees to 180 electrical degrees might take, say 50 milliseconds. I'm just giving a number out here. So in this particular case, calculating the area is a little bit more accurate, because at low speeds, the integration method generally works. You don't want to talk about the height, as I mentioned, because this is the voltage, and as I pulse with this, the height will change. So we can't basically talk about a specific height, but the area will always be a constant, because the area under the curve will always be a constant. If it's going very fast, then it'll be very steep, and if it's going very slow, then it'll be less steep. That's really it. But the area under the curve will always be the same. And that's the reason why we can talk about an area and then fix that area. And then say once it crosses that area, we know when to commutate or, switch the next MOSFET. But at very high speeds, this could, be very, very quick, to a point where by the time you sample the analog to digital converter, it might be a little too slow. And in order for us to prevent that, we can do something called a zero crossing method. So as soon as it crosses from positive to negative, we can start the switching cycle. So depending on the speed of the motor and the rotor, we can adjust based on low speeds. We can do the integration method, and with high speeds, we can do the zero crossing method. The thing why we don't want to have zero crossing methods at the low speed is because as soon as you switch, you need to have this time buffer, because you don't want to switch at this instance. You want to switch at this instance. So at low speeds, this could be, a very long time, and we want to prevent that. So the integration method allows us to switch more accurately, but at very high speeds, because it's so quick, by the time you actually turn it on, you'll probably reach here very quickly. So that's the reason why this horizontal axis is based on degrees, is not based on time, because the speed of the motor can be adjusted based on the voltage that you're feeding it, and the speed of the motor is adjusted based on the pulse width modulator. Those are the things that we want to keep in mind, and based on each angle, the electrical rotation basically works. Okay, so that's what we're trying to do over here. So in my microcontroller over here, when I'm programming this microcontroller, I would need few things to keep in mind. I need to activate my pulse width modulator, as I mentioned. I need to activate my analog to digital converter, so that I can basically measure the zero crossing or perform integration. I also need a timer, so that I know when to apply which method, low speed or high speed. So if it's taking, if it's going at very high speeds, the number of pulse width modulations would be very, very less. And if it's going at very low speeds, the number of pulse width modulations will be a lot more, because it's taking a longer time. And at the same time, it'll just be a lot more. So I can count the number of pulses that I'm basically triggering. So I could have a timer basically to figure out, when was the last commutation and the next commutation, for me to figure out, which methods to use, whether I want to use the low speed method or I want to use the high speed method. So that's the kind of algorithm that I'm trying to implement over here. There are a few things that this particular microcontroller has. It's got something called as a motor control PWM, because it knows that it accounts for dead time. A dead time is basically saying that I will not have this MOSFET and this MOSFET turned on at the same instance. And you can have these two MOSFETs turned on, the high side and low side turned on, because it can create a short circuit when you're switching very quickly. For in this example over here, in one of these examples, you could have an instance where these both are switched on, simultaneously very quickly, and it would create a short circuit. So a dead time allows that a buffer, making sure that won't happen. And that's really it. In this particular case, I've configured it this way, but it all depends on where the zero crossing is, because based on the configuration of the motor, this could be turning on first, and then as soon as this is turned on, then you could have the low side MOSFET with some other phase. Based on certain things will be rearranged based on the configuration of the motor and the position. So in this app note, as I mentioned over here, I do have my timing diagrams in here, and in here we have the 6-step commutation. And as I have over here 0 to 60 to 120 to 180 to 40 to 300 to 360, these are 6 steps. In here, this is how the 6 steps actually works. So you have the stator winding, which is the actual motor over here. And then you have the MOSFET switching high side, low side, high side, low side, high side, low side. So in the first step, the motor, the current will flow through the high side MOSFET, go through phase A winding, then come out to the phase B winding, and then switch and then flow through the low side of the phase B MOSFET. And while it's doing that, the rotor magnets will start to rotate. And while it's rotating, it will start to create a back EMF in the off side, on the off phase motor, on the off phase winding. And based on that winding, we'll then start to trigger sector 2. And then it'll go from the high side for phase A, and it'll create the phase B low side, phase C low side, and then the rotor will start spinning. And we keep doing this till we finish all 6 steps. And that's why it's called a 6-step commutation, or a trapezoidal commutation, because the voltage across the stator windings looks like a trapezoid. That's really it. And we do this till we activate all 6 of the MOSFETs. And once all 6 of the MOSFETs is activated, then we repeat the cycle again and again and again. That's really it. Yeah, my software, what I have over here, I'm using the McuXpresso IDE right now. Eventually, I will translate this and put this into my Linux repository. But for now, since I'm prototyping, I just wanted to show you what I have right now. So this is the enable wire, enable and reset for my microcontroller to start the pre-driver. These 4 wires is for the SPI communication. So in case if there's a fault or if there's some issues, the pre-driver can communicate with the microcontroller saying, hey, there's some issues. So and we communicate using SPI. So these are the 4 wires. And once we have the 4 wires, this is for the ADC. So the 3-phase ADC will be connected to the ADC of the LPC1769, which is the Cortex M3 processor. And then over here, I connected to the pulse width modulators. So based on which pin is pulse width modulated on this Cortex M3, I've connected the 6 wires for pulse width modulation. And the 6 wires is one for the high side MOSFET, low side MOSFET, high side MOSFET, low side MOSFET for phase A, phase B, phase C. So that's my connection over here. So we got ADC, we got SPI, we have PWM. So in a nutshell, what I've basically activated over here is on my main page. I'm just prototyping the idea and concepts right now while I'm designing the algorithms for this. The way I have started writing is I have a section for initializing and communicating with the pre-drivers. So I've basically put in the enable and reset pin so that I am able to reset the pre-driver or enable the pre-driver accordingly. This is the SPI configuration. So I'm initializing the SPI configuration. This is very specific to the microcontroller. So don't worry too much about what I've written over here. But I'm just talking about, how I'm going about designing and writing the code in order for us to implement this pre-driver. And then in this particular case, I've initialized the ADC. And then from here on, I'll start to initialize the PWM. And then I'll start to take readings and control the motor. Yeah, so I'm looking to get this done maybe in the next 1-2 weeks, time permitting. But yeah, that's about it. I hope this video was more informative. It's a little bit more dry, more theoretical. I hope I gave a decent explanation as to how this whole thing works, more from a perspective of if you're implementing your own, how would you go about doing it? If you want to know more about how I've done the pre-driver or how I've designed the pre-driver, you can definitely, check out the video on how I can design the pre-driver, which is all there in one of my video series. Yeah, so if you want to know how I designed the pre-driver or how I designed this particular chip right from the grounds up using, from procuring the chips to designing and the PCB and now fabricating and now testing it, I have a video for this particular microcontroller, how I've designed the pre-driver. It's all there in my channel. So yeah, I can put the links to below of how I've designed it below on the description. But yeah, thank you so much. If you find this informative, this is a vlog series. As I'm progressing, I'm planning to record how I'm doing what I'm doing. And if this is interesting, please subscribe. Do like the video, and even comment below if there's something that you want to know, or if there's something that I'm missing that you would do differently. Let me know. Until next time, stay safe.